Hello everyone and welcome to whatever this series happens to be. Basically, George just codes around and does some interesting stuff, hopefully, that you'll want to watch, or if not, well, we'll find out soon, I'm sure, when the views come in. In this series, we've been toying around with a project I have at work, which has to deal with a training simulation that's using the Oculus Quest 2. And last time I left off, I had done some work where I had gotten a system in place that allowed us to work with this handle over here, grab it, and then attach a virtual hand to it while still reading from the actual sensor data, and then allowing you to manipulate that by rotating it about a pivot point using the look at function inside of the transform. What we're going to do now is we're going to make it so that this is constrained between these two angles. We have a minimum and a maximum angle. If we open this object up, which we'll notice very quickly is that we have a min and max game object. Now this min and max game object, we're going to have to probably change how the system works because it's not really going to help us very much unless we record that data at the very beginning, because when we rotate the lever itself, the min and max are child objects and they will then rotate with it. So we can do two things. One, we can, of course, just delete them. We don't have to delete them, but why have extraneous stuff in your scene? And so we'll delete them out, and then we'll record the actual angles or the quaternion values or whatever we want to for that object at that particular time and place, or the vector maybe. We'll just use the forward vector. I really haven't given this a whole lot of thought how I want to handle this, so why don't we talk about how I envision it? And usually when I am trying to break down an issue or a problem, I simply go back to the basics. I talk to myself and I say, hey, George, what is it that we know? What operations are we familiar with? So if you've done some of your vector stuff, some of these operations are very easy. For instance, we have a max, right, and a min. So I'll put a min in blue. This might be opposite to what I have in the other scene, but it really doesn't matter. We just need something. So we have this max and a min, and we're going to label these V1 and V2 down here. Now, unfortunately, I am using a mouse. Sorry about that. And then we have some other vector coming out of here, and we'll just say this is S1, sensor vector, right? Now, when we want to compare vectors, what are the two operations that we really know about? Usually what we want to do is use either the cross product or the dot product. Now, the cross product is going to create either the area of the parallelogram, or it is going to end up, if you want to think of it a different way, it creates a vector that is normal to the other two vectors, and its orientation is determined by the order in which you do that operation. Now, that doesn't seem to really help us, but on the other hand, the dot product instead does provide us with a scalar value, a value between -1 and +1, and there's a cat behind me. However, we do have the dot product, which provides us with a scalar output and a value between -1 and +1, so long as we're using normalized vectors. You end up with a +1 when both vectors are parallel to each other. You end up with a -1 when they are anti-parallel, opposite directions, and then you end up with a value of 0 when they're at 90 degrees, right? So this was 0, this is -1, and this is +1. It's not going to be very helpful just as it is, because if we think about it, and I'm talking right now as if I know the outcome. I really don't. I'm going to be playing around it, but we want to do some sort of a comparison. But the comparison is kind of blind to the left or to the right side. We really want to know whether or not this S1 vector is to this side of V1. And we really want to know whether or not this S1 vector is to this side of V2. Well, how do we determine sides? What are things that we can start crafting with these two vectors? Well, what about vector addition, right? So if we were to add these two vectors together, and let's use a different color now. Like I said, I'm just talking through this. I don't know what I'm going to be doing, but this seems to make sense in my head. I've got a gut feeling that it'll work. So let's just do a vector coming out this direction, right? Now, I know that's not perfectly in the center, but you know, as every graphic is in every textbook, this is not to scale. Do not use them. Do not try to take a protractor and measure the angles. The idea here being that if we were to add V1 and V2, we would end up with a vector that goes, well, much further out. So we would have to do something like this. And where do I have my layers over here now, right? So this vector would actually go, like out to here, right? Now we would normalize this vector, and by normalizing that vector, you would actually end up with a vector like this. And if this was a circle, we would have our unit circle going all the way around, right? So if we were to take V1 and V2 together and average them, we would end up with a vector that perfectly divides those two right here. These two angles would end up being the same. Now, what can we do with that vector, right? Well, that vector kind of gives us a side, doesn't it? So let's think about this a little bit more. I'm going to hit F5 really fast. Let's fill this in with just some black because, why not? Let's go dark mode. Let's take our lever arm for a second, right? We have this lever arm. This lever arm's angle could be greater than 180 degrees, right? This lever arm could rotate this way to this way, right? But if we did that averaging thing I just talked about, right, and we added the two vectors together, so let's go ahead and do this, and we created this vector's on the wrong side. However, what's stopping us from multiplying this vector by -1? Absolutely nothing, George. Nothing's stopping us, right? Which would mean that this vector would then flip around to the opposite side. Let's just use a lovely green color instead, right? So in a sense now, we're kind of getting an idea of how we can manipulate things with vector mathematics. And I say we because I'm also figuring this out as I talk. So first, what can we do? Well, we can do an addition operator to give us an average or a half vector. I'm just going to say addition to get a half vector, right? Or we can put a line over top of that. We can then, if we wanted to, we can choose to flip it by using a negation, right? So we can negate that to then flip that vector to the opposite side. Great, so now we've got this other v. So let's just say v to the -1 right here, v to the negative first. We just talked about the dot product, but the problem with the dot product is it doesn't say sides. So all it can do is it can tell you really which side of a parallel or anti-parallel you happen to be are. So if we drew a line straight through this, like this way, right? And we were comparing this vector here with this vector, on this side, we're going to get a positive value. On the other side, we're going to get a negative value. That's all we really get from that. So how do we use that information then? Maybe we can use the cross product, right? The cross product would allow us to maybe take these vectors, multiply them by each other, and get a vector that is perpendicular to those vectors. We'll make this problem easy right now. V1, V1, V2, and then we've got our average vector, right? A instead. And then we also have some sensor data vector as well, right? So we'll do squiggles for that. Why not change our convention with every single thing I do? That's always nice, right? So then we have sensor 1, sensor data. If we were to take the dot product of sensor data with vector 1, what do we get? Well, when we're getting very close to V1, we're going to be getting a value pretty much at 1. But then when we go past V1, we're still going to be getting a value pretty close to 1. And in fact, we're not going to notice a change here until we're perpendicular to that vector, right? So this vector here is perpendicular to this one. And this is where we get the crossover. So we're positive over here, negative over here. Taking that again on this side, if we have V2, we're only going to start noticing a difference if we cross over here, positive here, negative over here. And what we really want to do is make sure that we fall into this range here. Thinking a little bit further, what if we extended this problem into 3 dimensions instead of this 2-dimensional one, right? So this one is, we'll kind of like give this a circled cap to kind of say, hey, that's 3-dimensional. So we got V2, right? And then we've got this one kind of coming out with a little thing there. We've got V1 again, and then somewhere in space is the other one, but we don't really care. What we do care about, though, is that from this, if we were to take the cross product, and depending upon the order in which we do it, it'll either pop out one way or the other, but we would end up with, we'll make a little line there, we could end up with another vector, right, the cross product vector, which could go either way. So the idea is that these are all perpendicular to each other at this point. Well, excuse me, this is not true. I'm sorry. This is not true at all. However, this vector here will be perpendicular to these other 2 vectors. Importantly now is if we were to take the cross product of this vector here, this new one, this cross product CPV, we'll just put that line over there so we know it's a vector so I don't have to keep, because I'm running out of V's and numbers, I don't want to do that. If we were to then take the cross product of this vector here and this vector here, we would then end up with a vector that is 90 degrees to all of them.
All of them.
This vector here that is now 90 degrees to these ones is going to end up being this vector right here. Similarly, if we were to do the same thing on the other side, we would end up with another vector. If we were to cross CP with V1, we would end up with another vector that is going to be 90 degrees to V1. So now we've got these vectors here and here that are perpendicular to V2 and then V1 as well. And if we were then to do a dot product of that original sensor data against these ones, well, now we are actually getting where the break is here. Are we not? I believe we are. So let's pick a differenter color. So what we're now doing is we should actually be doing a boundary that actually falls across V1 and V2. And those boundaries now should be positive on one side and negative on the other, positive on one side and negative on the other side. In which case now, if we do a check and we get all positive values or positive, negative, or however we end up doing this basically, we should be able to separate these ranges, right? Because this one's going to be positive, positive. this one on this one's going to be negative, negative, and these ones are going to be positive, negative, or negative, positive, depending upon what we think of. So at least in my head, I've kind of thought through the problem a little bit about how the vectors are and what they're doing, and I think I have some sort of a scheme to make this work. So why don't we actually try to visualize what's going on here by going into our lever class, and then we're going to go into our inverse grabbable class. And let's use the gizmos debug, or the gizmos functionality, to create these other vectors, visualize them in the scene, and actually see what's going to happen. So we're in inverse grabbable class, and actually, why don't we go ahead and close everything but the one we currently have open. So we're going to go here, let's do close all but this. And we'll zoom that up a little bit because the number one complaint on my channel is either I go too fast or the text is too small. So here we have our onDraw gizmos, and we're doing a minimum angle, and if this value does not equal null, we're going ahead and drawing it here. We're doing the same thing over here, and we have our blue and our red vector. So why don't we go ahead and do some of our math that we did. So that's going to be the min and max angle. Let's write some notes to us so we remember what we're doing, or so I remember, because trying to record a video and all this on the fly and get everything right is interesting. So we're going to go ahead and let's do an average center vector between, what is this, min and max. Cross product of the min and max angle. Okay, we're just going to visualize these and see if what I was thinking in my head ends up making sense in math land. Next up, so we did cross product of min and max angle. Then we're going to end up doing cross product of the XP. Let's just call it cross product. And why don't we do this? XP, Windows XP is going to be equal to that. We're going to say AV is going to be equal to that. And then we're going to say that min cross product is going to be equal to XP and min. And we'll also do max XP is going to be equal to XP and max. So before we are checking, so we should probably do the same thing. So we should do if min angle and max angle, right? We can then do a gizmos dot color is going to be equal to, we'll do yellow for right now, so color dot yellow. And next up, we can do a gizmos dot draw ray. Okay. Now, before we do that ray, we also need to calculate the darn thing. So why don't we just do a vector 3 average is going to be equal to our min angle plus our max angle, right? And we also then need to do something with this. So these are two vectors. I'm sorry, these are transforms. We want to do min angle dot forward and max angle dot forward as well. And then we're going to normalize this value. So we'll take both of these and we'll do dot normalize. Now that we have this average vector, we can take the position that we want this vector to stem from, which is actually going to probably be the same for all of them. But so here we're using min angle dot position and max angle dot position as if they were separate locations, when in reality, it should be this object. So this dot transform dot position's location, and then this is now the point off of that, which is going to be our average value. Okay, let's go ahead and save that. Let's come back over to the scene view. All right, so now we have our average vector that goes between these two. If we were to take that max angle and rotate it, you'll notice that that vector always will stay dead center. So that's kind of fun, right? Okay, so why don't we go ahead and make the rest of this stuff happen now that we saw that fun little thing. So we've done that. Let's do the cross product of these two angles. So let's just do, we're going to do this inside of here because if we've already checked to see if these exist, we might as well keep working with it, right? Let's do a vector 3 and we'll do XP is going to be equal to, and now we're going to take the two vectors up here, the min and the max angle, and we should probably do some sort of a check because we could potentially get a value of 0 if the angles were the same. But for right now, we'll ignore that. But we're going to take the min angle, and then we're also going to take into this the max angle as well. And then we can just do a vector 3 dot cross of those two. And we'll do the same thing again. We're going to draw this vector as well. And let's pick a different color as well. So once again, copying and pasting is fast, so why not do it? And ooh, you can do clear, completely transparent. RGB is 0, 0. That's interesting. So I guess that's a reset. I didn't know that existed. Why don't we do cyan? So we are going to do XP from the average location. We'll save that, jump back into Unity and take a look at what we've got. And there we go. So now we have our cross product of those two vectors. And the cool thing is, once again, the cross product is not going to change. So the cross product is not going to change. But you'll notice now that as we get closer and closer and closer, the value between them gets smaller and smaller and smaller. Remember, I had mentioned before that the cross product is actually the area of the parallelogram created by those two vectors. So that's actually a really awesome visualization if you're trying to understand what's really going on. As this gets larger and larger and larger, right, that area gets bigger, but then we hit a critical point at 90 degrees where then it continues to get smaller and smaller and smaller again because this parallelogram created by these two vectors gets smaller and smaller. So fun stuff. But what that really means is I need to normalize this value. So here we have average, but that got normalized. Here we have the cross product. So let's do cross product.normalized as well. Let's come back in over here into Unity. And now our vector will no longer change as the size, as this value is rotated. Now let's do these last two vectors to see what we have to play with. And we're going to grab this code again, and we're just going to paste it. And that's cross product. We'll do cross product min, and then we'll do cross product max. So we have some unique variable names. And then here we have the cross product of the minimum angle. And this time it's just going to be the min angle with the XP value. And this other one is going to be the max angle with the XP value here. Normalized as well. Our color should not be cyan though. Let's pick something else. So we had cyan already. What if we used a gray value for this one? And this one we can use a magenta. Why not? So then we need to replace the variable, right? Otherwise we're just drawing the same thing several times. So XP min and XP max, save both of them. Come back over to Unity. And now we've got our other vectors, right? So remember that the order actually will matter. And in this case, what we're getting here is, if we come back into our code very quickly, let's just actually comment this part out. Let's put that there, and then let's do this here and this there. So we just see one at a time. So now we're looking at the gray vector. So the magenta disappeared. And if we go to the min angle and rotate it, what we're going to see here is some interesting stuff happen. One, depending upon which side this min angle is on, it's going to cross over, right? But then if we do that, you'll notice also that this vector's orientation flip-flops around to the other side as well. Now we've got that gray vector shooting down here. And what is that gray vector? Well, that is going to end up being this minimum vector down here, the blue vector, right? Cross product with this cyan vector, creating this vector down there on that side. Okay, and you'll notice that that vector, that gray vector, is perpendicular to the blue vector. If we go to that max angle now and we start to rotate, well, nothing's happening here, but if we do crossover, you'll notice we get that nice little flip. Now let's try to get this one doing something that we like. So let's see, Unity, what are we dealing with? Left-handed, right? Left-handed stuff. So if we put our thumb down, I mean, you're going to have to imagine me, I'm looking at my screen, but if we put our thumb down the vector that we're multiplying by, right? So here we're dealing with the max one. And this is the maximum value, which is going to be this one right here, up here. So we took our thumb and shoved it down the max, which is the red one. So we'll put it down the red one, okay? And then the cross product with that, and let's see, what is the other one? The other one is going to be the cyan vector, right? So here's this one, here's this one. So this one's going to come out this way. If we actually switch the order and we wanted to keep the 90-degree angle on the other side for visualization purposes at the moment, if we flip-flop these and did XP first, I think we'll end up with something more visually pleasing. We can get rid of the comments. You know what, we might as well keep them. You never know when we'll need them. Future George is forgetful. And we'll come back here. Now we've got this red vector, right? Cross product with a cyan vector, which gives us this magenta vector coming out that side. So this, in essence, creates a vector or a line, which in our brains we can conceive of as a plane almost, cutting through space. And if this rotates, you can see that one keeping that order right there. And as this one gets closer and closer and closer, you'll notice that as these vectors become basically the same, they come together. And then they pop off to the other side, and then we can see the same thing happens over here. Although now, no, that's actually just fine, isn't it? Yeah. Now we need to actually do something interesting with this. So we're going to want to do the dot products of things and see where things end up on one side or the other. So to make things easy, why don't we create a new game object, just a temporary one for the moment, and we'll create an empty one. And we're going to stick it under this arm as well. And I'm just going to say this is called test vector, and it's going to point in an orientation. And this way I can move it around in the scene and see what happens. And let's put it under the lever as well. Now up here we did a serialized thing when we tried to find it. Down here we're going to do a similar thing, but yeah, let's just copy and paste these two lines. We'll do a serialized field, transform max angle, we will do instead, we call this test vector. So we'll do test vector is equal to null. So we have test vector. We can do the same thing down here. We try to do a find. We'll do a test vector is equal to transform.find, and we'll do test vector. I did not use a space, correct? I don't usually use spaces. No, good. Okay, so now we'll be able to find that test vector value, and that test vector is going to be a point in space. So let's first reset it. So coming up to the inspector, hit the reset value so it's back at the origin of its parent's transform location, or its parent's origin, which is its center point. Now we'll move this off somewhere here and somewhere up as well. Let's go ahead and visualize this. Now I'm trying to remember, I believe I can do like a stipple pattern or something, can I? So let's do a gizmos.draw. No, I can't. Let's just do a draw array, excuse me. Apparently I'm tired. And this array is going to be the same thing, this.transform.position, and it's going to end up at the actual location of that object. So coming over here, we'll do test vector, because remembering things is apparently not my strong suit at the moment. We'll do its position. So now we have test vector position. So that gets drawn. We'll just call this test vector. And we should probably colorize this as well. Let's do gizmos.color. We're running out of colors, right? Is it going to be color dot? Why don't we do black? It's a good one. We'll do black. It hasn't been used yet. Coming back down out of here, we're getting a bunch of errors. It is saying the variable test vector of inverse is not assigned. You probably need to assign it. Are we running? We're not running. Oh, why is it not working? It's because start only happens when it runs, right? And I don't want to do that whole test and executor mode or whatever. So let's just go to the lever itself. And for right now, let's go ahead and drag and drop it to test vector. Yay! Okay. So now we have a black vector going off into space, which is not correct. Why, you might ask? Well, that's because Ray is assuming this is the center point of where it's starting from, and this ends up being the direction of where it should go. So really, this position should be test vector.position minus this .transform.position. Back over here. And there is our black vector right there. If we were to select the grasping point right there. Nope, not test vector. There we are. We can see now that the test vector is on the end of that right there. So this is going to be basically mimicking our, what do you want to call it? Actually, let's make this a little bit easier to see. Why don't we do a gizmos dot draw sphere, something like that. And then that sphere can have a center point of test vector dot position. And its radius is, we want to make that small. We don't want it interfering with too much. Actually, can we do draw wireframe sphere? Draw wire sphere. There we are. Much better. We can go back over to Unity now. And we can see we have a nice, that's even pretty massive, isn't it? So let's do 0 to 5. So there we are. So now we have our tiny little object right there, our test vector that we can manipulate, and we can begin testing without actually bringing in any real sensor data to see what the outcome of this entire thing happens to be. So we've got a lot of stuff being drawn on the screen, and really I would love to take a little bit of time and maybe make this more sophisticated in terms of what we're making, maybe even have a mesh get drawn that will kind of create a fan that shows you the area that we're interested in. But just to get this over with, because the thunderstorm is still ongoing and I'm worried about losing power, we are going to just output things to the log instead. And as we move around, we'll get the sign of what we're doing, and we'll figure out which area that we need to work with is correct when we do a test. So why don't we go ahead and do some dot products now. Specifically, we're going to be doing dot products against the xpmin and xpmax with the vector here that we generated. So let's do a debug.log, and we're going to do a log against, we want to print out xpmin. Well, first let's do a vector3 dot product, right? And we're also going to want to do another one of these. So we'll do a .toString. We'll do a plus vector3 dot product there, .toString. We'll output both of those. And then we need to maybe make this a little bit nicer looking as well. So why don't we just do something like this and just say a comma in there. And then we can also do the same thing here. We'll put a parenthesis there, put a plus. We'll do a parenthesis on the other side and a plus just to make things look a little nice. So now the dot product will end up being xpmin, and it's going to be the other vector, which is the subtraction of these two. Might as well store this in a vector just for convenience. So let's do a vector3 And let's call this, what do we want to call this? Test vector, sure. Oh no, how about just TV test vector? It's going to be equal to this stuff right here. And then we're going to normalize this as well. So we have a vector that's normalized, normalized. So there's TV. There's this vector here as well that's being used to draw the ray. Then we're going to take the dot product of this vector and the dot product of XP max vector, and we'll do a TV against that as well. We'll come back down here. We'll clear this out for a second. And it's saying that I have something a little messed up. That's probably because I'm missing a parenthesis somewhere, and I am. Got a little parenthesis crazy. And we are printing stuff out. That's good. I'm just going to turn off everything else really fast, but these debug.logs. Let's clear it and see if it will follow it with us. So as we move this, what we're interested in seeing now are these crossover points, right? So here we've got a negative and a negative. We cross over here, we have a negative and a positive. We cross over here, we have a, let's see, negative and a negative still. Now we have a negative and a positive, and we come all the way over to here now, we'll have two positive values. Now we could do this however we want to. I would probably prefer to, what would I want actually? We like to be positive, right? Positivity is good. So maybe we should change how this is done so the output are all positives instead of negatives. Now the way I would assume we could do that might be, I'm wondering if we can do that just by changing the order of the initial cross product and do the, if this will do it, or if I actually need to do the order elsewhere. So let's do it there. Come back down here into Unity and see what happens. I'm going to clear that out really fast. And it looks like we've got double negative over here. And if we come around to between the two angles, we have two positives. And then there we have a negative and a positive. And there we also have a positive and a negative. So great, there we go. So we're going to need to test this to make sure it's robust and everything. But I do like the fact that I can now tell using positive and negative values whether or not I'm within these two vectors right here. So yeah, we crisscross over at negative. That's negative, positive, positive, negative, negative. That's all positive. See, that's a double negative. That is a positive, negative. That is a positive, positive. So I like this. We've done some very small initial testing. You know, if we sat down and we did the mathematics out, we could totally figure stuff out and probably do some unit testing as well. But, you know, when it's my own free time like this, I like to play around, and I especially like it to make it visual because I'm a very visual person. And seeing it work like this just gives me a better understanding of how the heck the math is actually working behind the scenes. So that's it for right now. This was a shorter video, but this was more of a test to get my setup working again. You'll notice the mic is a heck of a lot closer. I went back and reviewed a lot of my videos, and the audio was incredibly poor. So I spent, maybe 30 minutes trying to set things up, move things around, get my computer, which was normally over here on the side, down on the floor, so there's less fan noise and less feedback. I actually changed the settings on my mic so that the gain was lower. So now hopefully there's less, noise in the background that I have to process, and with less noise means less post-processing, which means my voice doesn't appear nearly as garbled as usual. I'll see you all next time. So long and goodbye.